Kinetic energy equation. The translational kinetic energy of an object is calculated using K equals 1/2 mv squared, where m is the object's mass and v is the speed of the object's center of mass. Note that kinetic energy can never be negative because the mass is always positive and velocity is squared, so even if you have a negative velocity, you're squaring negative times a negative becomes a positive. So note the square on the velocity, so speeding an object from 0 to 40 takes 4 times as much energy as going from 0 to 20. Get it? So if this was your final velocity was 40 to 20, your energy relation there. K equals 1/2 mv squared. That's what it looks like on the equation sheet. Nice and easy. Gravitational potential energy equation. Gravitational potential energy of an object, planet, system is calculated using the equation big U little g equals mass times acceleration due to gravity times y, where m is the mass, g is gravitational field, and the object is in, and y is the above a chosen reference point. The reference point for gravitational potential energy is chosen by you. So you get to decide where the height equals 0 is. You can move that up as it works for you. Usually you want it to go somewhere that's going to make your math easier. And it works because all we're doing is just looking at the total change in the energy. So if you want your height equals 0 on the table, do it. If you want height equals 0 on the ground, that's fine. Height equals 0 3 miles in the air, if that's what works, do it. The height y in the potential energy equation is measured from the reference point y equals 0 to the height of the object's center of mass. Note that an object by itself does not have gravitational potential energy. Gravitational potential energy belongs to the object Earth system, or object in whatever massive astronomical object is creating the gravitational field. So you need to have some kind of huge thing. You need a planet or a moon or a star to be part of the system in order to have gravitational potential energy. Otherwise, if you say, what is the gravitational potential energy of this marker? 0. What about now? Still 0. There is no potential to do anything. You were looking at this as just the marker. But if we include the gravitational potential energy, or if we were asked about the gravitational potential energy within the marker Earth system, then we could say it's something, and gets more as we go higher. On the AP exam, the equation is delta U little g equals mg delta y, because this equation is true no matter what the reference level y equals 0 is chosen. It's possible to have a negative gravitational potential energy if that object goes below your 0 height. For example, the object falls in a hole in the ground. We're now below y equals 0. There it is on the equation sheet. Note the equation is expressed in terms of change. We just talked about that. Elastic potential energy. The elastic potential energy of a spring is calculated using the equation U sub s equals 1/2 kx squared, where k is the spring constant. Remember that thing? It's the springiness of the spring. A high spring constant means it's very hard to compress or stretch. A low spring constant means it's a lot easier to compress or stretch. X is the length the spring is stretched or compressed from its natural length. If you just have a spring just sitting there at rest, then it's at equilibrium, x equals 0. So there's 0 spring potential energy. As you pull that spring, you're increasing the amount of potential energy because you're increasing the length that the spring is stretched. Potential energy is stored whether x is positive or negative, whether the spring is stretched or compressed from its natural length. Note that to compress a spring twice as much, it requires 4 times as much energy because of that square. Do not forget that the equation for force that a spring exerts is F sub s equals kx. Don't mix up the force equation with the potential energy equation. So you have F of s equals kx, that's Hooke's law. And then we have spring potential energy, which is 1/2 kx squared. The way that I remember that is You definitely know by now kinetic energy is 1/2 mv squared, right? And that's kinetic energy. So spring potential energy is going to be the one that kind of looks like that kinetic energy, 1/2 mv squared. I just make that connection in my brain. You do whatever works for you as long as you're not messing it up. Note the equation is right underneath the equation for force that a spring exerts. So you have your Hooke's law right here for the force a spring exerts, and then spring potential energy below that. And of course, by now your equation sheet looks different. So, sorry. Hopefully it doesn't look too different. Speaking to those in the future. Energy lost to friction. The only two forces that can take away kinetic energy and change it into dissipated forms of energy are kinetic friction and air resistance. Static friction can never change kinetic energy into any other form of energy. That means an object is not sliding, so it cannot lose kinetic energy to dissipated forms. If the object's not sliding, energy is not going anywhere. Kinetic friction or air resistance cannot change any sort of potential energy directly into thermal energy. These forces can only change kinetic energy into dissipated energy. If an object is sliding, the energy lost to dissipated forms is calculated using the equation E equals Fd, where E sub d is the amount of energy lost to dissipated forms. F sub F is the force of kinetic friction or air resistance acting on the object, and d is the distance that the object slides while the kinetic friction or air resistance acts. We've also talked about this as work being done to remove energy from the system. So this could be your negative work. If you think about it as your dissipated energy, just capital E, for the energy that you've lost, that will work when we get into the use of conservation of energy equation.